Okay, the next speaker, we will present a parity calibration, and the presenter is Chung, and it's a work with Rumack and Chirag Gupta. So, okay, thank you.
All right, thank you for coming to my talk. My name is Youngseog Chung. I'm a PhD student here at Carnegie Mellon University. And this is joint work with Rumack and Chirag Gupta, who are fantastic colleagues of mine in the same department here at CMU. So to motivate our setting, consider about a year and a half ago when the number of cases, COVID-19 cases in the US was increasing rapidly. I think many of us were wondering whether the situation would get better or worse. That is, would the number of cases decrease or increase? Oops. But specifically to a stakeholder, for example, a hospital that has to plan resources, or a policymaker that is instating restrictions, or an individual that's concerned about their livelihood. Knowing whether the number of cases will increase or decrease could be a much more useful measure of the future situation than the actual number of cases. That is, they are well aware of the current situation, and they can make better sense of the future situation in terms of whether it will improve or not. A similar example is the inflation rate, which is often measured with the consumer price index. As Fed Chair Mr. Jerome Powell said last week, of course, the Fed is interested in the absolute value of inflation, the raw value, but they're also interested in whether the trend of decrease that we've seen will continue. And this in turn will help them make their decision on further rate hikes. A similar case can be made for a bank that has to worry about economic forecasts or investments, or a household that is concerned about expenditures and price level pressures. These are all decision makers that could base their decision on whether some target time series will increase or decrease in the future. And with this, we propose the problem setting of parity calibration. And as a side note, we use the term parity here simply in terms of comparing two consecutive values, and it has nothing to do with fairness and no context there whatsoever. So we assume that we have sequential observations of real value targets, which are y, and any time step, we wish to predict whether the target observation will increase or decrease. If we denote the parity outcome with y tilde, which is the binary event of decrease, then the problem becomes producing calibrated predictions or parity probabilities p hat for the event y tilde. Of course, if you know the true CDF of yt at each time step t, then the optimal solution is to evaluate the CDF at the previous observation, yt minus 1, which will give you the true probability of decrease. But of course, we don't know the true CDF of yt. However, in many application settings, what we find ourselves is the modeling or the forecasting task is done by some domain expert. They hand off some expert forecast to the decision maker, who in our setting is concerned with parity probabilities and outcomes. To the domain expert, who may have no idea how their expert forecast will be used downstream, their focus will be on the regression problem, which is modeling the target time series y. And taking a probabilistic approach, they may produce a series of continuous probability distributions that reflect their best belief about what the value of the next observation should be, which we visualize here with a series of PDFs, which we can swap out with their corresponding CDFs. And with the CDFs, what we can see is the expert forecast with their probabilistic regression model actually has a naturally implied probability of decrease. We can evaluate their predictive CDFs at the previous observations, and this gives you basically the parity probabilities, p hat. But again, the domain expert doesn't know about the decision maker, and simply tries to do as best as they can on the probabilistic regression problem. One desirable metric, which was also mentioned by the previous speaker, is calibration, specifically regression calibration. So suppose the domain expert has tried to do as best as they can. They produced calibrated regression models. Then the question we ask is, do well-calibrated regression models produce well-calibrated parity probabilities? And there are multiple notions of calibration and regression. Just to really quickly recap how they're measured. One common notion is probabilistic or quantile calibration. And it's called quantile calibration because we usually assess calibration via predictive quantiles, which are in the dotted lines. And you ask the question, what proportion of the true observations fall below each quantile, where the true observations are the orange dots and the prediction is in blue. For example, you look at the 10% quantiles, see how many orange dots fell below that. Do the same for the 30% and a whole series of basically quantile levels. And you draw this mapping between predicted proportion under each quantile and the observed proportion of the observations falling under each quantile to produce a reliability diagram. And you want the blue curve basically to align with the diagonal line in orange. And of course, this is done over a held out evaluation data set. So that was calibration and regression. To briefly recap, calibration and classification or binary classification, where the outcome is discrete. And of course, the probabilities, the predicted probabilities are also over a discrete distribution space. You ask a similar question. For example, of all the instances I predicted 20%, did the event 1 occur 20% of the time? Then you would draw the same mapping as you see in the blue curve. And again, you want the predicted probabilities to align well with the observed probabilities. So going back to the question, do well-calibrated probabilistic regression models produce well-calibrated parity probabilities? And the short answer is no. And this answer holds for many common and well-known notions of calibration and regression, including probabilistic or quantile calibration, which we just looked at, distribution calibration, which is a stronger notion of calibration and regression, and also threshold calibration, which is a more recently proposed notion of calibration tied with decision-making. And this plot shows an example from one of our empirical case studies that visualizes how this discrepancy can take place. So in the top half of the plot, we see the target time series, YT, and a probabilistic regression model that is represented with prediction intervals in blue. And we can see that the observations in orange are actually well contained within the prediction intervals. And this is actually very well quantile calibrated, which you see in the reliability diagram on the right. At the same time, we can shade in the regions in the top half with red, where the parity outcome was 1. That is where the target time series, the orange dots, decreased. On the bottom half of the plot, we are tracing the implied parity probabilities from the blue predictions in the red line. And we can shade also with the shade of red, where there was a high probability, a predicted probability of decrease or a high parity probability. And to achieve parity calibration, you would want these red shades in the bottom half and the top half to align well. You want, when you predict a high probability of decrease, for the target time series to actually decrease. But we see that they are not well aligned, which is also evident in the reliability diagram for parity probabilities on the far right. And I just wanted to make a remark of how bad this is. Usually for any level of miscalibration, you would still see a positive slope in the calibration curve, but we actually see a negative slope. So the predictions and observations were actually completely opposite. Whenever you predicted a high probability, the true probability was really low. So intuitively, this mismatch can occur because in a regression setting, we assume that each data point is IID or comes from a batch with no notion of sequence whatsoever. Whereas in parity calibration, the aspect or notion of sequence is actually really crucial. So the expert forecaster can be parity miscalibrated despite calibration and regression, but it still remains the reason that the expert forecaster can provide valuable information through the predictions, and that we can still use it by refining it or calibrating it further. So to this end, we note that the problem of parity calibration is in fact one of binary calibration. And binary post-hoc calibration is a well-studied problem. But since we're in the sequential prediction setting, we should learn an online post-hoc mapping, MT, for adaptivity to distribution shifts and drifts. So given pre-hoc forecasts or parity probabilities from the expert forecaster, we can calibrate them to produce better parity calibrated post-hoc probabilities. So there are many binary calibration algorithms out there, and in our work, we chose to focus on the class of algorithms known as Platt scaling, which learns a mapping from probability space to probability space with two parameters A and B, they're scalars. And these A and B parameters are learned by optimizing a loss function, usually the log loss on a held out calibration data set. But again, we're in the online or sequential prediction setting, so it makes sense to adapt them to the online setting. And as a naive baseline, one thing we can do is to introduce windows of the recent history. We can have a moving window or an increasing window, where a moving window simply means you move a recent history of the predictions and data points, and you continuously refit your A and B parameters as you make more observations. Whereas increasing window is basically anchoring the beginning point of your window and accumulating all of the data, observations and predictions you've seen so far, and updating your A and B parameters with all of the data. So those are the naive baselines. Another algorithm that we propose using in our work is a recently proposed algorithm based on one of our own works, recent works called online Platt scaling, which reframes the problem of online learning Platt scaling parameters as online logistic regression, where the features here are one-dimensional. They're the pre-hoc or uncalibrated probabilities. And online Platt scaling, or OPS, aims to minimize the regret in terms of the log loss with respect to the best Platt scaling parameters in hindsight. So some comparisons between the two possible methods that we've introduced so far for the problem of parity calibration. The windowed Platt scaling methods, they can incur up to t squared computational complexity, while OPS makes constant time updates at each time step. So they're linear, O of t. Further, windowed Platt scaling has no guarantees on regret, whereas OPS provides sublinear regret in terms of the log loss with respect to the Platt scaling model class. To demonstrate how these methods perform for parity calibration, let's go back to the COVID-19 case study that we opened with. In this setting, we can take as expert forecast the COVID-19 forecast hub, which in collaboration with the Delphi group here at CMU, produces real-time continuous distribution forecasts for the number of cases in the US for each week. And taking their regression forecast as the expert forecast, we actually see their parity probabilities are not as well calibrated. You see the blue curve that is not as well aligned to the orange diagonal line. Further, a lot of their predictions are sort of uninformative. They're 0.5, basically saying, I don't know. And after applying OPS, we see that parity calibration improves significantly. The blue curve is aligned much better to the diagonal line. Further, the predictions become much more dispersed and informative. That is, they become sharper. Another empirical result we can show quickly is from weather forecasting. You should recall the example on the left side that we took a look at. It's actually from it's actually the pressure signal from a baseline benchmark weather forecasting task, the full time series of which over many years you see on the right. Again, the base regression forecaster or the expert regression model is quantile calibrated, but terribly parity miscalibrated. Applying moving window, increasing window, and OPS all improve their parity calibration. But OPS is best at improving parity calibration, further the sharpness of the predictions as well. So some higher level takeaways from this work that we believe may be of interest to the audience, in specifically in uncertainty quantification, is that parity calibration is one notion where we can connect notions of calibration and regression and classification. And in our case, the interpretation can also be of interest to a decision maker. We'd like to invite the community to tackle this problem together, not just confined to parity calibration, but just getting a better understanding of the connections for calibration and regression and classification. Another idea is that post-hoc calibration can be thought of as a way to focus the capacities and capabilities of a large general model to a specific use case. For example, the expert must have done something useful and actually provides a prediction that is rich with information with full distributional forecasts at each time step. And we can further refine this model to a specific use case with a simpler goal, which in our case was binary classification for parity outcomes. One last thing I'd like to quickly tell you about is that many of the nice plots and the metrics that were used for this work were made with the Uncertainty Toolbox, which is a Python library for practitioners and researchers in predictive uncertainty that myself and some colleagues here made together. I'd like to recommend this package to those interested to try it out. And thank you for listening. My poster session is later this afternoon, so please stop by. Thanks.
Thank you very much. The discussant is also online. Oh, okay, please.
Hi, everyone. Thank you for the very nice talk. So I will start with a few takeaways that I got from your paper that you summarized just earlier. So you show in your paper that having calibrated regression is not enough to have parity calibration. And that, however, starting from your CDF, you can calibrate the probabilities p hat using methods stemming from binary classification, here flat scaling, to have calibrated parity calibration. Parity calibration. So I have three questions for you. The first one is if you could give us some motivation on why you chose to focus on flat scaling, and why not, if you could compare with other methods such as temperature scaling or histogram binning or other methods like that, if they could do better or worse, in your opinion. My second question is intuitively, once we have calibrated the probabilities for the parity, that the higher or more extreme probability implies that the difference between YT and YT minus 1 will be higher. And then my last question is, what do you think of extending your work to predicting for higher time steps? Do you think that it might be more complicated due to the non-stationarity of your data distribution?
Yeah, thank you for the very insightful questions and also this, the nice summary of the paper. We chose to, regarding the first question, we chose to focus on plot scaling because it was actually by chance that the algorithm OPS, online plot scaling, was proposed around the same time with one of my coworkers, also one of the co-authors on this paper. And it provided really nice guarantees, especially in the online setting with respect to one very popular class of post-hoc calibration methods and classification. But as the discussant mentioned, you can, of course, use other online adaptations of other algorithms, such as histogram binning. In one of our ablation studies, we also did try a naive online adaptation of histogram binning with moving and increasing windows, and they also seem to perform on par with the moving window and increasing window versions of plot scaling. But the focus of this paper was really to introduce this connection and reduction of regression calibration to binary calibration. So that's why we proposed focusing on plot scaling. The second question is very, it's very sharp. As in, I think that's actually one limitation of our method, is that it doesn't really say anything about the magnitude of increase or decrease. It simply says about the binary event of increase or decrease. So of course, in many settings, for example, investing, trading, you of course care about the magnitude. You don't just care about going up or down. You could go up and then just lose it all in one time step if the decrease is really large. So no, it has no ramifications about the magnitude of increase or decrease. About the last point, I think it's a valid point, taking relative comparisons between multiple time steps instead of just consecutive ones. We really didn't venture into this much for our work, but I think it's very valid. If you set a constant to k, I think you could almost do a naive adaptation of all of the methods presented to that problem setting.
Great. Thank you very much. So we have time for one question. Over there.
Okay, thank you. This was a most interesting talk. And in the interest of time, I'll just go and ask the question. This refers to an expansion to the last question of the discussant. You could possibly extend your p hat or your y tilde to be the probability of y decreasing or increasing by a certain margin, fixed threshold. Is this something that you could do easily?
Yeah, I think it's something that you can easily just model with the proposed method OPS. It's just a matter of setting really the threshold and defining what the outcome is for the binary event. Ours was just increase or decrease, but if you set a threshold, you could easily apply it to that setting as well. Yeah, thank you.